pretty sure I have that meeting. Oh, it's on. Yes. So, we're starting in on chapter 27 on carbohydrates. And today's lecture is about 90% vocabulary. A certain part of me says I should skip it and just tell you to read the book, but if we don't have the vocabulary, then we start talking about all the other stuff, and it doesn't make any sense anyway. Plus, it's a nice, easy topic. It kind of gets us started on a Monday morning. So first off, what is a carbohydrate? That's a common enough term that you should have encountered it in high school, maybe if you took nutrition class, or have any idea what the food pyramid is. What is a carbohydrate? Okay, some examples are bread. What are some other examples of carbs? Noodles. Or pasta. What else? Wheat, anything made with wheat or flour. So what's in common with all these though? So you know what types of foods are carbohydrates, but gluten? Well, gluten, I don't know actually if gluten is a carbohydrate or if it's more like a binder for stuff like that. Actually, we should put that. We'll have to look up what gluten really looks like, since I don't actually know. Okay, so it's in a bunch of other things. We can also include it in basically anything that contains sugar, lactose. So milk has a good chunk of carbohydrates in it. And then basically plant materials. So chemically what a carbohydrate is it's a polyhydroxy. What does that mean? Polyhydroxy aldehyde or ketone. And poly just means many. And hydroxy, we remember, means OH. And so basically it's a molecule that contains a large number of OHs and has an aldehyde or a ketone functional group sometimes, someplace in it. The term carbohydrate actually comes from the belief originally, so this is somewhat true, that the formula was CnH2O to the N, meaning that they were carbon or carbohydrates, because hydrate means kind of H2O and carbo kind of means carbon. And really that is kind of the formula, but it's a misleading way to write the formula because we don't actually have water units attached to the carbons. We have OH groups, which is our alcohol functional group. And so they really have the generalized formula CN, usually H to the 2N, O to the N. Good morning, Jasmine. Make sure you get a copy of the lab and the homework that I forgot to print out earlier, and a copy of the cheat sheet that you guys get to use on a test for carbohydrates over there. Yeah, maybe I forgot to, maybe that was buried under the rest of the piles. I forget. I don't know. But basically, I've handed out now all of Chapter 26 and Chapter 27 homework. Chapter 26, there's A through D. Chapter 27, there's A through what? E? F? E? Someplace in there. And so, if we take a look at what a typical carbohydrate looks like, it's usually 6 carbons, 1, 2, 3, 4, 5, 6, although there are plenty more. We've got a aldehyde functional group, and then almost all of the other carbons in that molecule will have OH groups attached. And so if we look at it, and we remember from last chapter, oops, not that last one, sorry, I should be careful. Notice that there are 4 chiral carbons in the molecule. Therefore, there's 16 stereoisomers for just your basic 6 carbohydrate with 6 carbons in it. So we've got a number of different classifications, and the first one we can call is how many carbohydrate units we have. And so the first one is we can have what's called a monosaccharid. I hate spelling this word, saccharid. And that simply means that there's one carbohydrate. And then, of course, we can have two, which is going to be called disaccharids. And later on, I should say, we'll talk about the three most common monosaccharids. We'll talk about the three most common disaccharids. There is a middle ground that is sometimes included, and they're called oligosaccharids. Oh, and di, of course, is 2. Oligosaccharids can be anywhere from 3 to 10, and I'm going to put a question mark on that 10 part, meaning that different books will define that differently. Some books might say it's only, 3 to 6. Some might say it's 3 to 8. Some might say it's 3 to 20. That number pretty much varies, but the general idea being it's some sort of intermediate level of carbohydrate. And then, of course, the last category is just polysaccharids. And for our case, we'll just define it as 11 plus, but there's usually upwards of hundreds of these little molecules stuck or stitched together. And we'll talk about, now I'm going to lose or forget, I can't remember if we talk about 3 or if there's 4 common polysaccharids. I can't remember which way it is now. Oh, C to the N, H to the 2N, O to the N. And that's a generalized formula. There are ones that will differ from that, but that's sort of the most common or average formula when we're talking about those. So we can classify carbohydrates by the number of carbohydrates units present. You guys watching the fly around? I know. I saw a mosquito earlier. It's like, yeah, I know. Okay, we can also categorize them according to the number of carbons present. I should point out that this next test, there's a good chunk of it that's simply vocabulary, making sure you define things properly. So if there's 3 carbons, we call those a triose. 4 carbons is a tetrose. What do you think 5 carbons is? Pentose. 6 carbons is hexose. 7 carbons is heptose. And I imagine that pattern goes on, but what we find is that the vast majority are 5 carbons and 6 carbons. We will occasionally talk about, got my foot stuck in the cord again. I don't even know why I sit like that. The 3 and the 4 carbons, because they're precursors to building up the larger molecules. But in general, we don't talk about any of them. So we can categorize them on the number of carbons. And I should point out, when we do lab next week on Tuesday, and I don't know, we might do it this week on Thursday, we might not. Depends on how motivated we are. We might start it because the carbohydrate lab is really long. And so if you can get some of it done Thursday, some of it done Tuesday, and some of it done the following Thursday, it'll be good. One of the things that we do is we have tests to distinguish between all these things. So we can tell the difference between a 5-carbon sugar and a 6-carbon sugar with a test. What, Jasmine? Well, you know what I mean, the next week of classes. Kind of like when we say the next lab, it's due the next, the following lab period, that means, Thursday. Or if I say the next, this is due the next lecture period, that means Wednesday. So yes, when I say next week, we mean the week after spring break, right? So functional group. If we have an aldehyde as our functional group, we call that an aldose. And if we have a ketone as our functional group, we call that a ketose. I don't know why, and I don't know if it's just human nature or if it's just biologists in general, but, you know, and maybe it's chemists that came late to the game, but we tend to have the same thing but many different names. So if someone said, oh, that's an aldehyde, or if they're a biologist, they might say it's got a bunch of OH groups that's also attached to it, they'd call that an aldose. Why they have to come up with their own names for everything, I don't know. I liked the original names that we had for those already. So we can have functional groups. We can have different stereoisomers. And the primary one that's important to differentiate between is the D or L isomer. And this is somewhat confusing, especially since we do it right after 26. D and L are not equal to dextro and levo rotary. So they're just, I don't know if it's an unfortunate coincidence. I don't know where the D and L nomenclature came from in biology, but it doesn't mean that it rotates plane polarized light to the left or plane polarized light to the right. And in fact, what we find is that you can't tell how a sugar, or any molecule for that matter, rotates plane polarized light. Rotates plane polarized light. Meaning that some sugars will rotate or have it be considered a plus, and some sugars will have it be considered a minus, and we won't know which is which until we do it. Oh, that's right, I forgot to turn my alarm clock off from the weekend. So the weekend I said, Jay, you can sleep till 8 o'clock. And it was glorious. And then I forgot to shut it off for the rest of the week. So the definitions for D and L isomers for carbohydrates is it's the orientation around the carbon, the carbon furthest from the most oxidized end. And we'll draw a picture of this in a second. And I think the picture is probably worth 10 times the amount of words. If the OH is on the left, we call that the L isomer. If the OH is on the right, we call that the D isomer. And again, I'll draw a picture here in a second after you get all these words down. I should have left more room, gone to a new slide, something like that. Here will be Fisher projection. So one of the things you're going to realize is that the Fisher projections we learned in last chapter, we're going to be drawing lots and lots of those in this chapter. Did you have a question, Aaron? Just go ahead and ask, and I'll repeat what I said instead of asking Taylor. That doesn't get us anywhere, because I don't want to talk over you, and I don't want to just go on and leave you in the dust. So feel free to ask. So if I draw two stereoisomers, and since these are aldehydes, we'll put the aldehyde group at the end, and like that, and then I can have the same or similar molecule like this. There's a double bond O. So H, OH, like this. And I should point out that after a while, Jay gets lazy, and he tends to only draw the OHs on the molecule. But for now, we'll draw the H's too. So we call this D-glucose. on this side, and this is considered the L isomer or L-glucose. And the difference noticed between D-glucose and L-glucose is the orientation around the last carbon atom there. And the reason we make this distinction, the reason we care about whether something is the D isomer of the molecule or the L isomer of the molecule, is it turns out that this is the only one your body uses. So your body only uses the D isomers. Only uses or recognizes the D isomers. Recognizes the D isomers. So Jay's quick and dirty, weight loss program says that we should just make foods with all the L isomers. Your body wouldn't even recognize it, and it would pass right through you. The what? Well, that is probably the bad part of this, is that if your body doesn't recognize and digest it terribly well, then it probably literally goes straight through like that. Have you guys heard of Olestra? Hmm?
That ally stuff where you sell it at Walmart. I can't remember if that's the color of the stuff that you sprinkle on, but it makes your body not digest it, so it literally.
Yeah, so Olestra, I'll draw the structure up later. I don't know where it is in my notes. It's basically a fake sugar, and instead of having the sugar on there, they throw on some big long chain fatty acids, and your body, of course, doesn't recognize it. And so it's a way to have the taste of sugar, but not have your body digest it and get the calories from the sugar. No, that's a different way to do it. So anyway, well, okay, let's do one at a time. So for instance, the Olestra, of course, just goes right through your body, and of course on the warning label is all these nasty things like, can cause diarrhea and all this huge long laundry list of stuff, to where it's like, I'll just eat the fat and get fat instead of eat the non-fat stuff and crap my pants. Trevia and some of those other sugar substitutes, they try to interact with the sweet sensation on your taste bud with a different functional group than what the sugars do. And so yeah, they try to find something that your body won't digest and turn into energy or storage of energy and do it that way. So a lot of the sugar substitutes also have, some part of their chemical formula looks like a sugar so that it can bind to the taste bud or the receptor, and then the rest of it is something your body won't recognize and digest, and that way you don't have any calories associated with it. That, and they can also find stuff that tastes, 10,000 times sweeter too. So you have to use, 10,000 times less of it. So even if your body does absorb it as calories, you've had 10,000 times less, which means you can eat 10,000 cookies instead of one. That's a pretty damn good deal, I think. If it wasn't for the butter and the 10 million other bad things that are also in cookies. So your body only recognizes and uses D isomers. So one of the reasons we have a chapter on stereochemistry is so that we recognize what we're talking about when we talk about these different types of isomers. And also, to me, it's pretty amazing that simply changing the side that an OH group is on a molecule is enough to make your body not use it or your body not recognize it. So it turns out that your body, and this is going to be kind of repeated over and over again in these chapters here when we look at different molecules, is very, very sensitive to the actual very specific shape of a molecule. And if the molecule doesn't look right, then your body rejects it completely. Well, I don't know if I'd say completely, but it doesn't go through. Okay, one of the unique properties, what number are we on anyway? 5? Yeah. I should just number them better in my notes. Number 5 are ring structures. And to kind of give you the straight up definition before we get going, so that you kind of have it in the front part of your notes and you don't have to go looking for it, if it makes a 5-member ring, then we call this a furanose. And molecules that tend to make furanoses are ones that have aldehydes or ketone functional groups plus an OH that's 4 carbons away. And we won't worry about these so much, so I'm going to put a little asterisk here that says we won't draw these very often. there's only one five-membered, there's fructose that's a five-membered ring, and then there's ribose that's a five-membered ring. And so we'll learn to look at them, know them, recognize them, but we won't practice drawing them very much. And then, of course, the other way that we can do it is we can make a five-membered ring, and we call that molecule a pyranose. So the main distinction, what we're trying to focus on, is the difference between a pyranose and a pyranose, and that's if it's an aldehyde or a ketone functional group, plus the OH has to be 5 carbons away. And so what really happens is that sugars, or maybe I should use the more technical term, carbohydrates, exist in two forms. The first form is the linear or chain molecule. And then the second form is usually a ring form. And the ring form is formed because we take an aldehyde plus an OH group, so an alcohol, maybe I should write it that way. And what does an aldehyde plus an alcohol make? Does anyone remember? See, this is where, if you remember the stuff, no, carboxylic acids, where if we oxidized an alcohol to an aldehyde to a carboxylic acid, but if I add them together, it's a, not an ester, not an ether, hemiacetal. And of course, if it's a ketone version, it makes a hemi. And if it's the second, if it's a hemiacetal and a hemiketol plus another OH group, what does it make? Ketols and acetals. And so these reactions from chapter 23 and chapter 24, guess what, show up on this test. And so if you remember the reactions from chapter 23 and 24, you're golden. Life's pretty easy. If you don't remember those reactions so much, then you're not so golden. So let's, go ahead.
On that top part where it says 5 carbons away and 4 carbons away
From the aldehyde or the ketone. I'll draw a picture next. We're going to illustrate this. So let's make a pyranose. How to draw ring structures. And technically, a ring structure is called a Haworth structure. So just like we have Fisher projections for showing enantiomers, we have what are called Haworth drawings or Haworth structures or Haworth, whatever you want to call them, for how to draw the cyclic structures. So let's draw. Now this is also in your book. So, and do I have a page number for it? Nah, it would have been too silly to throw that in my notes. We'll just look at it like this. So here's my D-glucose. And if I number the carbons, and maybe we'll switch to another color to number that, you know, we always start at the top, 1, 2, 3, 4, 5, and 6. What we're saying is that the number 1 or that aldehyde can react with that OH group. So this is, so basically it's an aldehyde plus the OH group 5 carbons away. And so that's going to react to form our, oops, that's not supposed to be a little smiley face, to make a hemiacetal. And so here's my example of, I don't even know if this is glucose anymore. I've taken it apart and rebuilt it so long. I guess we could kind of look at it. Let's see. I got an OH on the right-hand side, OH on the left-hand side. Oop, this isn't glucose, but that's okay. It works good enough. So what happens is that aldehyde functional group, and then our chain can rotate around. And if it rotates around, what we notice is that the carbon, that OH group on the number 5 is perfectly aligned to interact with or react with that OH group on the number 1, or that aldehyde on the number 1 carbon, okay? So what we're going to do is we're going to rotate that molecule around. And so the best way I can think about it is it's like felling a tree. We just take this molecule and we just lay it down kind of like this. And so if we're kind of drawing this, and we'll never draw this intermediate step very often, but I'm going to draw it the first time. So if I look at my molecule and I bend it around like this. So here's my aldehyde. Here's an OH group, and this OH needs to be pointing up then. This OH needs to point down. This is my, what a pain in the butt. I'm looking at my picture and it's drawn wrong, so we'll just ignore it. Must have done it for something different. OH, OH, OH. Here's a CH2OH, and there's an OH. So I kind of over-exaggerated that last bond. Let's draw it a little closer like that. So if I'm numbering that again, because it's very important to keep track of my numbers, here's 1, 2, 3, 4, 5, and the number 6 is pointing straight up, right? And so what we're saying is that we can rotate this molecule around so that this OH and that aldehyde are my aldehyde plus OH. And of course that goes to make a hemiacetal. And so here's the picture that you'll be drawing lots and lots. Oops. Come on. So it's kind of a hexagon laying on its side. The features that are always going to be the same is that if it's a D-isomer, the number 6 carbon points up. Now, we said that there are L-isomers, right? And your body doesn't use the L-isomers, so we'll never ever draw the L-isomer. You might see it drawn occasionally where that OH is down, or that CH2OH group is down. That really indicates the L-isomer. Although I have to be honest, you really have to be careful if they draw it a different way. Some places, and in some instances, you can have it pointing down. We will never do that. We'll only draw D-isomers because there's no point in trying to confuse you guys by drawing L-isomers that don't exist. So this is an oxygen right here on that carbon. And then this OH and this OH and this OH stay up and down. And then this OH here can be either down, let's see, I got to remember this, beta up, alpha down, in which case we're going to call this the alpha anomer. Or if that same ring closes, then I can draw a second molecule that's very closely related to the first one. In fact, all of the parts are the same except for one, and that's that OH points up. And so here we call this, if it's pointing up, the beta anomer. And the way I have to remember this is Buddha, beta, up, down, alpha. Or the other one I sometimes remember is BAUD, but do you guys even know what a BAUD is? B-A-U-D? Yeah, so never mind. Meaning that's a geeky internet type term, but everyone knows who the Buddha is, right? So you can remember beta, up, down, alpha. At least that's how I remember, because it's a 50-50 thing, right? And so what we're saying is that when that ring closes, that new OH group that's formed for our hemiacetal can either have that OH pointing up or that OH pointing down. And here's where it's, I don't know, I won't say it's silly, but your body can tell the difference. Your body knows the difference between a beta and an alpha. Your body knows the difference between a D and an L isomer. Your body cares about tiny little things like this. And so guess what? That means we have to care, right? As chemists and biologists and things like that. So, you know, all these pictures, if you're not careful, all start to look alike. And so what you have to focus on is what's going to be different. And what we're always going to focus on is this carbon right here, and whether that OH group is up or down for about 99% of what we're drawing. So, oh, I wanted to point out one other thing, just so we have it here. That carbon and that carbon, that's where our hemiacetal is, right? And see, we're going to care whether something's a hemiacetal or not, because hemiacetals react one way and acetals react a different way, just like they do in chemistry. We have a special term for those two ring structures. It's called an anomer. And anomers are basically two isomers that differ in the orientation of the OH on the carbon, or on the hemiacetal carbon. We'll just say it that way, hemiacetal carbon. And realize that that hemiacetal can also be a hemiacetal, or that's what I just said, hemiketol. It can also be an acetal or a ketol. And sometimes that's even given a special name. That's considered the carbon that's capable of mutarotation. So mutarotation is the ability of the OH group on the hemiacetal, etc., to open and close and interconvert between beta and alpha. And so that hemiacetal carbon turns out to be really important. It's where most of the chemistry occurs, and it's where we have to really pay attention to whether something's beta or alpha, because if it's the beta anomer, we'll learn that, for instance, in polysaccharides, now I'm going to get it reversed. I forget which one is which. One of them makes cellulose, and one of them makes starch. And starch is, of course, good for you. It's the primary component of French fries, potato chips, and all sorts of goodness. And cellulose is what we make trees out of, and grass and stuff like that, not terribly tasty. So your body can differentiate between that alpha anomer and that beta anomer. So we're focusing here on really little details, aren't we? And so you have to know and be able to pick out these really little details on your homework, and you have to know and be able to pick out these really little details on your tests, of course.
Did you say the equivalent to sign with beta or is it alpha?
The equivalent to what?
Well, we use that sign.
Oh, yes. So alpha and equivalent to are the same symbol, right? And they mean different things. Just like, for instance, an alpha and a beta we also talked about alpha and beta hydrogens, right? When we're talking about doing the aldol reaction. That means something different than when we talk about the alpha and beta anomers when we're drawing ring structures. Okay, we can do the exact same thing for a 5-membered ring, and we'll just draw it really quickly. Again, I'm not going to have you do these on a test. If you can master how to do the 6-membered rings, that's good enough. Since there's only 2 of these that matter, and you're given them on the chart and your cheat sheet and stuff, you won't really ever have to use them. So notice that here I have a ketone, and that ketone is going to react with the hydrogen on the numbers 5 carbons away. So let's see, it's 1, 2, 3, 4. So 4 away in this case. And so that can interconvert in between making a ring structure that has 5 carbons, so that's our pentagon type shape. We stick an O there, we stick an HO, CH2 there, we have a CH2OH here, we have an OH here, and we have an OH here, for instance. Oh, wait, gotta have one here too. Sorry. Everybody's gets an OH, right? And so, if I number this molecule, 1, 2, 3, 4, 5, and 6, then we start here, 1, 2, 3, 4, 5, and 6. And so this is an example of furanose. And of course, that carbon can be either alpha or beta, depending upon if that OH group is pointing up or that OH group is pointing down when it makes the ring. So let's see, we talked about anomers, Buddha, alpha, beta, blah, blah, blah. And let's see, we got, oh, man, I have lots of these pictures in here. That's good, you guys get lots of help. Remember, I have flashcards and stuff like that. Please go check them out. The idea is not for you guys to just print the flashcards out and study the flashcards necessarily. I did them because students one year were way into making flashcards, and then they kept asking me, well, is this good or bad, or how much should I put on this or that? And I kept telling them, it's up to you. This is what I would put on a flashcard so that I can study the material. What you guys should look at and decide is how much you need to put on your own flashcard. I think the purpose of flashcards and the purpose of, like, you know, like when people print off slides from a talk and try to study those, that's okay. That does cover the main points. But if you put it in your own words, if you make your own flashcards, if you make your own notes, you'll find that it sticks better in your brain because you're processing it, right? You know, go ahead and use them. Say, okay, I like that one, or boy, that one's a little crowded. I'm going to break it up into 2 different things and things like that. Okay, we have something called epimers. So we got lots and lots of words. And this is 2 monosaccharides that differ in the configuration around a single carbon atom. Oh, this is a new one. What number are we on? 6, 7, 6, 8, 9, 10, who knows? 2 monosaccharides that differ in the orientation around a single chiral carbon. And so if we look at it, because there's 4 chiral carbons in all the molecules that we're going to be talking about for the most part, then there are 4 different epimers that we can draw. If we pick a nice easy molecule, D-allose, I should point out, does J have the structure of D-allose memorized? Hell no. J doesn't even have glucose memorized. You'd think he'd probably have memorized that after teaching this class like 50 bajillion times, but he doesn't. Instead, that's what the cheat sheet's for. I want you guys to use that cheat sheet to, you know, shortcut things like this. And so all the molecules that we're drawing today, they're on your cheat sheet. You don't have to memorize any of the names or do anything like that. You just have to be able to recognize features on them. And so if I switch the OH groups, for instance, if I take that one and I switch it, then I've got another stereoisomer. And this is called Dgalactose. And I can keep doing that. If I switch the second one, oops, I guess I've got to finish off my molecules. I'm being a little lazy here and just leaving off the parts that are the same, like the CH2 groups and the ketone groups and stuff like that. Then I get OH, 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 and a HO, and I get D-glucose. If I do the third one, And the parts are the same. CH2, OH, 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 a HO, and an OH. I get D-gluose, not gluose, gulose. And then, of course, I can switch the bottom one. O bond O, CH2OH. I get a HO and a bunch of OHs. And this one, notice because this last OH is on the left side, this is the L isomer, so we call this L-talose. And so notice that for any given molecule, we can have 4 epimers.
That second to last one, is that with a G or is that an F?
That's a G, gulose. So glucose and gulose look the same. The only thing difference is kind of the L and the U are flip-flopped and things like that. And there's actually a C in glucose too, but I don't know. Don't sit like that, Jay. You're just going to break things. Let's see. We already talked about how to draw Pyranose and Furanose rings. Boy, are we already on that? We're really cruising ahead that far and fast. We are cruising. Cruising for a bruising. I guess I haven't given as many examples as I do sometimes, and I did skip this whole section here. So let's go back and cover that section. So these are the different ways that we can talk about and different terms we're going to use. So you're going to notice that we're going to use all these terms. We'll talk about hemiacetals, hemiketols, acetals, and ketols a lot. When you get practice doing the homework and you start picking up on the patterns of where they are in the molecule, you'll realize they're not too hard to pick out, but you do need to know those definitions from chapter 23 and 24. That's why we put them in those, or well, I didn't put them there. That's why they're in those chapters, because there's something that comes back. We're going to be using the terms pyranose and furanose quite frequently. We'll use terms like aldose and ketose when we're describing things, and we'll use terms like pentose and hexose when we're talking about the number of carbons. So there's a lot of vocabulary that we need to know so that when we're talking about different features of these molecules, we're all on the same page. Okay, so what are some important monosaccharides? So the first one we can talk about is D-glucose. And I don't know if you really need to draw the structure here. Again, you guys will never be held responsible for memorizing the structure. But it is not a horrible idea to draw a bunch of these, because by drawing them all, you start to see how closely related they are to each other, and that I find it amazing that your body can tell the difference apart. It's like trying to look at Chinese people and telling the difference between them. I mean, it's hard, but apparently your body can do it, so I'll bet you we could learn to do it too. Yes, I'm a racist. All Chinese look alike, but they make amazing food and they do an amazing job on your laundry.
On the laundry?
Yeah, all the laundromats are like Chinese people.
I don't know, dry center was right?
Well, around here it's all Mexicans, I have to admit, but it's all Mexicans in Montrose. Anyway, aside from making fun of Chinese people for looking alike, we should focus on this. So D-glucose is the most common monosaccharide. We will be seeing this molecule over and over again. It shows up in many, many chapters, and we have an entire chapter on how we digest and transform glucose into energy and energy storage. It's found in fruits, vegetables, honey, etc. And it's the fundamental building block, or it's 1/2 of sucrose, lactose, and maltose. And these are disaccharides. so we'll talk about them next. And so glucose really is kind of like the standard 4x4 or 4x2 Lego building block, in that it's part of every other molecule that we're going to talk in this chapter. It's the primary component of starch, cellulose, and glycogen, which are the polysaccharides that we'll talk about. And it is featured in the metabolism chapter, in chapter 34. So we're going to be seeing glucose ad nauseum. Okay, the second most common monosaccharide. Whoa, I had to write a bunch of words, yeah. I gotta teach you guys, we should teach you guys shorthand, how to write fast. It's a beautiful talent in life. No. Everyone should take debate in high school and have to be able to write down enough notes to be able to refute an argument in a speech. And that really teaches you to write super fast. Because, I don't know, and I think it's kind of silly, but debate in high school was half about how fast you could talk. Because the faster you could talk, the less time the other team had to write down stuff. And so sometimes it became a contest in speed more than a contest in persuasion, which is what I think a debate really should be. How many people took debate in high school? Yeah, that's what I thought. You had to give a speech? Did you do Lincoln Douglas speech, extemporaneous, anything? See, I think every kid should take those classes. I think that's as important as playing a sport in high school to a certain extent, because being able to get up and talk in front of a group of people and be comfortable in it, that's the beginnings of it. Just being comfortable, just giving a speech, being able to speak. How many of you guys would consider speech in college to be your most feared class? Everyone here is pretty comfy. A lot of times, I literally will have people tell me, can I put that off till the last semester because I'm afraid? And I'm like, so you're okay with taking chemistry, microbiology, and A&P, but you're afraid of speech? Because some people just have a big fear of public speaking.
I talked pretty much in front of the whole time, and I was terrified. My legs were shaking so bad, and I read, but I got done pretty quick, so I could get out of there.
Well, my general theory on speaking is, if you're practicing your speech for speech class, if it takes you 8 minutes when you practice, it'll take you 4 minutes when you actually do it, because you'll talk twice as fast, at least.
Well, I knew that I was going to talk fast, and I tried to pay attention and slow down, but it was so scary.
I'll also admit that it depends on your audience. Dgalactose. For instance, talking in class like this, I don't get too nervous, but I'll bet you if I had to get up and talk in front of the entire college, I might be a little more nervous. Or if I had to get up and talk in front of the town or the high school or anything else but, my classroom where I'm pretty comfortable with things. So Dgalactose looks like this for comparison's sake. And it's an aldehyde. We've got a CH2OH group on the bottom. And, if you're not paying attention, and I'll be honest, if I didn't have my cheat sheet, if you told me that something was D-glucose and then you told me something else was D-galactose, I wouldn't have any clue what the real difference between the two was. Notice that it is an epimer of glucose. And some interesting facts about it is the second most common. Actually, it might be third. Never mind, I lied. Third. And it does not occur as a monomer. In nature, it only occurs as part of lactose. So galactose is one of those things that you need to get in your diet. And so if you're lactose intolerant, sometimes you can actually be deficient in Dgalactose. It's used in cellular membranes. So we're going to be seeing it again when we talk about various things like that and the nervous system. And we talk and we see these in glycolipids and glycoproteins. And that's in chapter 28 and I think 29. So we're going to be seeing these molecules again. It's nice if you can kind of recognize them. And for instance, the galactosemia, sorry, I have to pause to spell when I'm talking. Galactosemia is the inability to metabolize lactose, the inability and it can lead to things like cataracts, mental retardation, and cirrhosis of the liver. So your body, we're also going to learn that no one's body is perfect. We all have some chemical reaction, or maybe we should really say biological reaction, that your body doesn't perform like it should. Just a second, Alyssa. And what we find is that, this isn't one example of it. And usually, or quite often, there's a backup mechanism in your body that can help you. But sometimes these deficiencies or these inabilities of your bodies to metabolize a specific compound or to build or make a specific compound has to be remedied from outside sources. Alyssa?
What?
Cirrhosis. Yeah, notice that I really kind of slaughtered the spelling there probably, and who knows if that's spelled right. And really, you'll notice that my handwriting usually gets really bad when I have to spell something I don't know how to spell very well, or if I'm just lazy or in a hurry, then my spelling gets kind of ugly too, or my printing does, I guess. So Dgalactose is the second one. Notice that the combination of glucose plus galactose are the only two isomers that matter. Meaning that there's 14 other isomers of these molecules that your body completely 100% ignores. It obviously ignores all the L isomers because your body doesn't even recognize them. And then the other 6 isomers your body doesn't make use of either. I think it's pretty impressive that, your body is actually smart enough or sensitive enough or something to actually pick out small, tiny differences in structure. Okay, number 3 is DFructose. And it is an example of a ketohexose. So notice that it has a ketone functional group. And so it actually ends up being one short for stereoisomers than what we'd expect. And so there's only 8 stereoisomers of this molecule, of which your body only cares about the specific one, DFructose. Oops, I guess, what was I doing? Oh, that's just funny. I was like, I wrote something below it last time. Well, I wrote Dgalactose twice, so that doesn't make any difference. So it's the sweetest carbohydrate. It's approximately twice as sweet as sugar, or what we call sucrose. And so just pure DFructose is actually a better sugar substitute than sugar. It's 1/2 of sucrose, and that's a disaccharide. So remember, what we're going to do when we make these disaccharides and polysaccharides is we're going to take these monosaccharides, this glucose, galactose, and fructose, we're we're going to interact, or we're going to have a chemical reaction between them, and we're going to form the disaccharides or polysaccharides. So we're going to have to know and kind of understand how that chemical reaction occurs. However, it's probably one of the easiest chemical reactions. All of the molecules are being put together by dehydration reactions, we'll learn. So again, don't forget your chemistry from previous chapters. So you need to know your hemiacetals and your hemiketols and how that works. And we're also going to have to know our dehydration reactions for a lot of things. Your body generally converts it to sucrose. Generally converted to glucose. So one of the things we're also going to learn in our body is that your body likes to deal with one molecule. So for instance, your body's primary molecule is glucose, or one of, I should point out, is for carbohydrates it's glucose, for fatty acids and things it's other molecules. And so your body takes things like DFructose and immediately turns it into glucose. Your body takes Dgalactose and for the most part converts it straight to D-glucose. And then it can enter into the metabolism. And we'll learn about all that details in chapter 34. So your body tends to like to have sort of one or two key molecules into which it can convert everything. That keeps it from duplicating a bunch of chemical processes for each molecule. Since again, your body has basically one enzyme per chemical reaction or per thing that we need to do. Let's see, where are we in our notes? My notes for these chapters are kind of atrocious. They are all over the place, and you know, the nice thing about it is it doesn't really matter what order we put things in. It's all about the same. So we'll cover one last, let's not cover it. We'll save it for whatever day, Wednesday. So let's say that on Tuesday, remember the pre-lab for the IR lab, which is number 31. Wednesday, let's do 27A, and I don't have my homework here. I don't know if you can do 27B yet even. I think you probably potentially can. Who's got a copy of their homework handy? I think I'd have the answer key sitting right here. Oh, here it is. Except I've switched them around. And you should be able to do, if you're kind of trying to, you should be able to do 27B also. So let's say 27A and B are due. I think you can do both of those on Wednesday. And then Thursday, we'll also do the IR lab. That's the handout we just gave you today. It's not in the lab book. I wrote that up over the weekend. If people want extra credit, I'll bet you there's like 500 spelling errors in it. The lab I just handed out, there's probably loads and loads and loads of typos, spelling errors, units missing, units wrong, words spelled wrong, numbers wrong, who knows, there's probably loads and loads of it. And then also, I guess on Tuesday we also said you should also have 26 B, C, and D due. And 26A was due on Friday. There's a pile for it there. I didn't grade it over the weekend, so if you slip it into that pile, I won't even notice that it's late. That's it for me. Jess